Main work is to simulate the system. We don't close. It's so difficult.
How are we recorded? So I will not put any comment.
And like doing this proof seems very hard to me.
For us, I think it's very good. Yeah. Because we didn't have any, and I am like fretting on the other front. Nothing used to go on right now. Okay, so we found to last time. We'll finally at our three objects. Typically, is D or D comma D. Green is the set of vertical, D is the set of edges. Any comma B will be complete respect of the graph. Any questions before we begin? Last time what we tried to show that we tried usually that P of n would have to be log n over n. Then the time is also written as 0 of n comma. That's what we showed last. But I was waiting and waiting and waiting for some of you to object to this step. This is a meaningless result until I show something. What did I prove? That is lambda was greater than 1 something. Lambda was greater than 1 something. What if I keep going down or something? So if I keep changing P of n, I don't show any monotonicity property. That as P n increases, if a property happens, it continues to hold always. No, I didn't follow. So we got a graph. This statement I said is that P of n is larger than some quantity, some property goes to higher order. If P of n is smaller than something, this property goes to higher order. But this really makes sense. I need something that if I increase the probability, if an event happens, it continues to happen. If I reduce the probability, if it doesn't happen, it continues to not happen.
But log n by n is the threshold, we already know that, right?
So, say this result is fine. Okay. I show something for lambda greater than something. If I don't have monotonicity, that is, if let's suppose event E happens. Some value of P. If it continue to happen, okay, so let's say P equal to P prime, and P is equal to P double prime, and P double prime is greater than P. It's only when such threshold results make sense. That if I keep increasing, eventually I'll get something. If I keep reducing, I'll eventually not get something.
So I didn't get this. Even E happens for P equal to P prime.
Some value of P prime. Does it continue to happen if I increase the probability?
Okay, okay. So that P double prime should be what greater than E. Yeah. Okay.
None of your objective. This is something we would like to learn. Otherwise, the meaning of threshold doesn't make any sense. Until some point, something doesn't happen, and just beyond that, something starts to happen. Yes. So if you increase, I mean, after threshold, but if I don't have this property, is it meaning? What do you feel going to select? that for no value of P it happens?
I mean, isn't it already implied in the threshold?
How? If I don't have this, how?
Like, I mean, let's say you have this quantity and you are saying that you fix the threshold.
Yes.
Once you cross the threshold, it should continue.
That's precisely what I'm asking for. You have to show me that.
Okay, I just know that.
This is one point. That it doesn't happen. At particular probability, it continues to happen if I increase the probability. So there is an underlying probability within the graph concept. Essentially, you fix a P of n, you fix a particular value and say something else. Now for every P larger than, all of this makes sense, only if it continues to hold.
Yeah.
What if the behavior is oscillating?
I see.
Non-intuitive. That should happen, but who knows? You would have constructed an object for which there is no monotonicity.
So what you are demanding is that your Pn should have monotonicity in its nature or something.
There are certain events for which there will be monotonicity. Certain events there will be no monotonicity.
So
The
if you
events
don't
we are trying to find are essentially having paths. Think about that.
what? Yeah, essentially having.
Paths between two events.
Okay.
So an event, really, let's take an example, P to be the event. Then there is a bar between some two vertices V1 and V2. Or everything is bidirectional. So now suppose this is my event. Does it satisfy this property? Very simple event. We did something like this to say, if you remember, Bernoulli with probability P and Bernoulli with probability P prime, where P prime is larger than P, are stochastically dominant, if you remember.
Yeah.
How do you do? It's not easy to do, right? But so think of binomial, for example, binomial of n comma p and binomial of n comma p prime. You would like to say something when p prime is larger than p. If you toss coins, you will not always see something. But stochastically, something should happen that p prime is stronger than p. So what was the argument? We did something called coupling. We're hammering on coupling for a long time. So on the side, if you remember, consider two random variables, x and y. This is y. Let's say n comma p, and let's say p. Care about p. Now, what do you expect x and y to translate? You think that y is in some sense larger than x.
Yeah, stochastically dominant.
Right. So how do we prove this? We prove this.
Yeah.
So generate a single random variable. So instead of looking at x, you generate an x prime. And instead of y, you get y prime.
Yeah, the couple.
So x prime and y prime are coupling x comma y.
Yeah.
What is x prime? So you generate a single random variable. Let's say u. Let's say u is a uniform random variable between 0 and 1. Now, depending on u, can I define x prime and y prime such that they are correctly denoted? Sorry, they have the same distribution as x. But it's obvious that y prime is stronger than x. You can have multiple copies of this. You need multiple copies. So how do I generate an x prime which has the same distribution as x using multiple uniformly identical copies of u? So suppose n is 1. There is just a Bernoulli random. Now how do you do? Then you don't take more than one copy. So think of n equal to 1. Now here x prime is an indicator as long as u is less than p. This is the indicator u is less than p. That's the indicator. So indicator means it's equal to 1. If u is less than equal to p, it's 0 otherwise. Now does it have the same distribution as x? What is the distribution of X prime? Just tell me that. Is it Bernoulli with probability P? Okay, something is missing. What is the distribution of X prime? What is the distribution of U? So what is the probability with X prime takes value 1? As long as this is less than P, and that is probability Q. So the probability of X prime being equal to 1 is P. Probability of X prime being equal to 0 is everything else. But it's same as this, and then equal to 1. Similarly, this is the same distribution of 1. Now tell me what is the relationship between X prime and Y. Here I cannot compare. So the two distinct random variables I can. Now there is something very strong. Can you say that X prime is always smaller than Y prime?
If P prime is one, then
No, whenever this is 1, this is always.
yes.
That's all. So here I could not gain this, but now I can. And I still have the same problem. So essentially I can transfer the pattern. This is the, and we have a proof that if I can create a coupling, which is essentially always less than equal. So if I would create X prime and Y prime, where X prime is less than equal to Y prime, surely, then X is dominated by Y.
Yeah.
This is the result. Now take arbitrary n. All you need to do is to take n copies of this, n identical copies. So you can divide this to be summation. Let me call it. Or not this. That way. Like this. R is coming. Now again, this relationship works. The X prime is always smaller than that.
Yes.
That has the same distribution as X prime. So I have X is stochastically dominated by Y. So something like this is what I want. You tell me there's nothing, no there is no difference. So now, if E is my event, then there exists a path between U and G. As I increase P, what happens? So P is my event, then there exists a path between U and D. Suppose it happens for P equal to P prime. And if I increase P prime to go to P double prime, what can you say? You have to use the same idea as this guy.
There will be a higher probability of being a path between U and B. So basically,
So give me the complete instance. What you're saying is right. I gave you an explicit description of showing X is dominated by Y. You tell me the same thing that gives event with P and P prime and P double prime dominate. That's all you wish. That if there is a better probability of this happening with P prime, the probability only increases if I go from P prime to P double. That's all you wish. Once it is clear what we are after, something very simple but needs to be done. Use the same idea, exactly the same idea. So what is the randomness now? In this example, what was the randomness?
U from 0.
No, that was in between stuff we created for us to show that this is. Currently, what do we have? We have a G and P, right? What do we have? We have a G and P prime. We have a G and P double prime. Right. Where P double prime. That's all we have. All I'm asking you is giving me a coupling so that I can show that this is getting dominated. That's what we will see the same example. So what is the random process for each pair of vertices? Tossing a coin, making it one with probability. P prime there and P double prime there. How is it any different?
It's by
This and this. Can we just nail it exactly? There's no difference. You just have to do it more times. Essentially, it's not different at all. So take a pair of vertices. U, B. Just tell me what do I need to do for each pair. Use the uniform random variation.
Uniform random variable, I suppose.
So let's suppose you have a uniform random variable. Belong to 0, 1. Yes.
If it is less than P, then you have 21.
Okay.
Otherwise, it has one. So P prime.
No, I want to couple this P and P. That is one way of generating. You are telling me one way of generating this graph. Correct. What I want is somehow compare these two graphs. So what you're suggesting is exactly the right way of generating this graph. For each pair of vertices, just toss a coin. If it falls below P, you can make it 1. If it falls above, you make it. Right? Don't do it. I want to somehow cover these two things. Use the same idea. What did I do? Created a new graph, essentially. X prime and Y prime. Okay, what did I do? I coupled their outcomes. If this was 1, this was always 1. Why can't I do that here? So instead of G L P prime, why can't I do it? G prime or L P prime? P double prime and P double. Making sure that G and G prime are the same. So this and this should have the same distribution, because they should have the same distribution. How should I go from here to here? Using a uniform random variable. For each pair, I put a vertex. So in this graph, I put an edge. Should I do this? No, that's a little trouble. That's what G was generated.
Yeah.
I want to generate G prime and somehow couple G. So I could say, let me represent X as a random variable for the presence or an absence of an edge between U and make it 1. No, so that would not. So let's call this X will be indicate that a uniform random variable is less than this valid definition that an edge between U and V exists as long as U is less than equal to V. Okay. Similarly, let's call it Y U that corresponds to G double prime. And do the same thing. V less than P double. Exactly the same construction. Now, result is correlation. XUV is always smaller than YUV. And what is the distribution of XUV? It's the same distribution as how I generated G and P prime. So if you are comfortable with this, there is actually no difference between what I'm doing. Here, you take n equal to 1. Every edge is drawn independently. So I don't have to worry about different edges of the system. All I'm saying is the Bernoulli P probability event. This is nothing but a Bernoulli with P prime and a Bernoulli with P double. That's all. So if you just are happy with this, then I can do this for n equal to 1. You can do the same. Do nothing else. It's just something not clear. Which is doing everything pairwise. Everything is independent across the graph. If you really think of a pair of vertices, all you're doing is drawing a Bernoulli random variable probability. If I increase the probability, all I want to find is a coupling for which, if an edge exists with P prime, it should also exist with P double. So it's exactly the same as before. There's no change. And I can do this h by s because the graph by definition is independent across different vertices.
So I got it how we defined XUV and YUV, but means how we are associating them with G dash and G double
This
dash.
is exactly how I'm generating the level.
Okay.
For each edge I go and I generate an edge with this probability. Whenever this is 1, I put an edge, whenever it's 0, there is no edge.
Okay.
And there is the same distribution as now.
How is G and G prime? They are not different, right?
They're different in the way I'm generating them, that's all. So you should ask all my questions here. I'm not doing anything with it. So if X and X prime different, well, yes, because it's a very different way of generating the numbers. You could do whatever you want to generate this. I'm doing this one particular way of generating this. All I'm ensuring is that they have the same distribution. But at the same time, I'm essentially making a connection between X prime and Y. Here they are independent, how you generate, I don't know. Okay. Here I'm generating one particular way by coupling these X prime and Y. That is all it is. All I'm associating is a common random variable, which is a uniform random variable, depending on its outcome and coupling the value.
Okay. Could you give another example where we could generate this graph?
Which graph?
This
Another distribution of G.
yeah.
P.
How you want to generate?
No, so this is one way of generating this graph, G and P.
Correct.
G prime is one way of doing it. Can you give one more example? Like I always thought that this is how we generate this graph. No?
This is how you do it.
This
So it's just the fact that you want to put a connection between you and me or
yes.
it will be
So it's, yeah, this is the most obvious way of doing it. See, the point is not that this is the one way of doing it. What I've done is the more important.
Yes.
That the same U is controlling the generation of both the graphs. I would have kept U1 and U2. That also will give you the same graph without having any connection between them.
Yes.
That's precisely how G and the G there is generated. All I'm doing is inserting the same U to generate something which is correlated. That is all I've done. So you can put as many U's as you like, you get the same distribution of G, as many identical copies of it.
I mean, you can generate couplings different ways, but you, at the end of the day, you want to compare them.
So by keeping the same U here, I'm able to get something. If I want to keep independent copies of U here, I will not get anything. That is exactly these two functions, which are independent of this. It is relatively implied. Most of these models, this is not really used. That if a path exists with probability, when the underlying probability is P prime, that path should also exist when the probability is P prime. The probability should not exist. That's all. Yes. It's not true that always it will happen. It could happen that with a larger probability, some realizations are bad realizations. That's okay. That's all we have is a stochastic number. Okay. Okay, what the is useful even outside of this course.
Yeah.
One thing.
Yes.
So like when you say that you are making this distribution larger than the previous one, like this is P prime greater than P. So like you are taking So you're basically saying that if you have a distribution, let's say to begin with, which is P of n, and now you're taking another distribution P prime n, and it might happen that for that distribution you will not generate connectivity. When the graphs, the points are not connected. Can you give me an example for that?
This is the opposite. What are we saying by doing this? Like suppose there is connectivity. Let's precise. The probability of connectivity. Under letter is after that. That is all we are saying. Realization, the realization, things will be very different. It's not always, even if you take two uniform random variables, one has been one, sorry, one has been half, another has been 2/3. It's not always that the 2/3 will always show a value higher than half. The probability which shows is larger value is larger. This is all we want. Okay. So once I show something for P of n, it continues to hold everything about. Yes. And if I continue to show, I may show you something negative about the value of P of n, it continues to hold for any value which is smaller than. This is what we do. There's no comparison in realization. The book has a weird way of saying, let me say informal and formal. Well, the event happens in the graph. So then it continues to happen. If I keep the same edge, I can't disturb that edge. If I add another edge, that's all it is. So increasing the number of edges, but not increasing. It has to be super. So the number of edges, this is just a thing like that. So the set of edges is simply 1, 1, 2. Okay. 1, 2, 3. What is it here? 1, 4. So if some event happens when S is true, it continues to hold when S prime is true, when S prime is true. That is what it says. Every event is not increasing.
It seems why they can
Think about it. You can get every event, even in this simple graphs, not increasing. Just complement it. Whatever you're thinking is complement.
One example would be if I ask the event 4 is disconnected. 4 is disconnected, and then the next set
It's not true. Okay. If I increase the number of edges, it could be that 4 becomes connected. So not every event is increasing or every event is decreasing. An event is defined to be increasing if I go from a set of edges and increase its flow superset. And stretching the
Yeah,
flow superset.
it depends on the what event you actually.
Exactly. So an event can be increasing. The reverse direction is called decreasing.
But I make connection like 3, 4, then it is not.
If I were to make 3 here,
No, yeah.
here,
Hmm.
now they are not even comparable.
Yeah.
They are to first of all comparable. This way of writing is pretty bad. I like the forward. That's what. Why I'm doing this because to give you an inequality which most likely will not use in the book, will not in the course, but it's a very powerful book. So, a more brutal definition of the same. Let probability space. An event is very element that is called an event. And I usually take that A. Really clear about all these things. You think of taking that A happens. That's what indicator is. So A is indicator A. Omega is an element of the omega. Less than equal to indicator A of the prime. There will be the prime number of elements of the outcomes. And that's about it. You're worried about this word partial, just think of it. Your omega and omega prime are ordered. So what every time omega is smaller than omega prime, if A happens with omega, it always happens with omega.
So A is your event.
A is an event. Okay. Omega is set of outcomes.
Yes.
Set of outcomes determine where A happens. So if omega is less than equal to omega prime for some order, and the event happens with omega,
What is the indicator of A in this?
indicator is the event happens.
Yeah, same. Yeah, okay.
Something written more formal. So indicator 1A less than equal to indicator. This actually is the random variable. So this takes value 1 or 0. So it's always less than equal to the value it takes for every pair omega prime that satisfies.
I see.
That's actually a real number. That's why I can compare.
How is ordering defined between the outcomes?
Whatever it is. This is a brutal definition. Now you define them, you order it, and with respect to that ordering, this will be engineering multiplication.
Okay.
So it's up to you forward. In here, it will be clear.
No, what is omega again? I'm sorry.
Well, you set up outcomes.
Some kind of outcome.
An element belongs. Omega, omega prime, both belong.
So you are defining and auditing the outcomes.
For whatever order you may want to. So now we have an example of an increasing event for our graph. You should already event was increasing. I'm asking for one event. So this is the heart of how we define all the couplings. Remember this. Now what I'm taking a single random variable. Whenever it's greater than equal to P, I'm turning this one. Whenever I'm turning less than equal to this. So what kind of event is what's going on here? What event is increasing?
the event of having a edge between the two.
Oh, so now we define an event for me in the graph or whatever. What do you see? What is the omega and omega prime correspond to in the graph? Set of edges. So the way I define S and S prime, the S prime is a superset of S. So that is clearly satisfies the condition that omega and omega prime belong to my outcomes. So define any event for which this is always true. But if I see more edges, the event should continue to hold.
Is it, I mean, you can just define number of edges. Okay.
Yeah. Okay. But number of edges is not an event. Number of edges is equal to something.
Yeah.
That is, so that's an example. So number of edges equal to k. Is an increasing event. If the probability increases, it only increases. Similarly, finding a path between two fixed two vertices.
Yeah.
It only increases.
Yeah.
So, but not every event is increasing. We define the complement event.
Yeah, that's as it defined. Yeah.
There are so many ways in which you can define. So here we clear. Most likely don't use so. Okay. The three organs. The two came together and then one wrote separately. The K is for castaneer. Declaring incredible amount of strong results attributed to it. This is false. False. Let me know. But inequality is as follows. That if it is best. It goes by the name if AG inequality. You know Cauchy torch is equality. Cauchy torch is how powerful it is. This is equally powerful, but requires some condition. And goes to the reverse direction. That's the utility. Cauchy torch gives an upper bound, this gives you if A and B are both increasing or both reducing. Both increasing or decreasing events, then utility of AB is very good. That's how strong this is. So AB means A intersection. We find it through the many standard ways. Try to find a counterexample. It's a good exercise. That if the events are not increasing and decreasing simultaneously, what goes wrong? This is actually not true. It is very strong. We did not can't appreciate it right now, how strong this is. Because you should not expect this to happen. Think about it. This is a product, and this is an intersection. Should not expect this to. This probability should actually be smaller than this.
Yeah. Intuitively, one thing that.
That's why it was strong. So
If set A is completely contained in the B, then this would.
they're equal.
Yes.
Not really.
A contained in B.
No, so the A intersection B is just B. While P of A could be not trivial.
And A contained B, A intersection B.
B.
Yeah.
Then this would hold.
While P of A could be something smaller. Yeah, so you're right. It will still hold. But that is a special, it doesn't even require any of this. It's not even asking for any such. It's asking that both A and B could be arbitrary events. As long as they're both increasing or both decreasing. Both going in the same direction. It can't be that one is increasing, the other is decreasing, then you can't realize. This decide, look for a proof issue. I really interested. I have found it useful in my own work many times. When you get stuck, lower bound is something, always comes to yes. Very strong. Okay, now let's go back to our brochure. So now we write GLP starting from a particular vertex, something like branching process. we'll try to define three types of vertices: active, inactive, neutral. To begin with, at 0, B is the only active. Or define 0 to be.
What is X0?
This will be clear. It's actually another active.
Okay.
V or V not? V.
There is no X.
So just starting at one point. All I am interested in looking at the connected component of V. I want to write.
Okay, so how do you define active mode? Okay, stop.
At time 0 is that. Everybody else is neutral. At time t, some set of vertices are active. Okay, so let's call that. Some are neutral. What I will do is I'll arbitrarily pick any of the active nodes. So let's call this W. And explore all possible vertices which are neutral and have an edge to them. So suppose here is an edge, here is an edge. Dot means there is an edge. Okay. One thing want to keep it completely vacant is important. So it's easier. Put a dotted edge. There is no edge. Let this be an edge. So there are essentially three possible edges again. So now what do? I make this guy active, this guy active, this guy active, and this guy inactive. And I keep doing this at each time. But each time P, I go to one of the active vertices currently.
So at each time, the number of nodes, number of nodes at all times are fixed, right?
Total number is that. It is changing the status.
Okay.
Each
Connectivity is also fixed.
edges are fixed. I'm not
Edges
edges
are
are
fixed. Okay.
I'm just defining active, neutral, and negative. That's all I'm doing. So neutral edge after getting explored becomes active, and active gets inactive.
Inactive. Okay.
So each fixed time, I just go and arbitrarily pick one active one and explore all its neighbors, which are in the neutral state.
So active can connect with the neutral always.
Active can connect to neutral. What does it mean?
I mean, when W becomes inactive,
Yes, there is over.
then
You need to tell connect.
So the rule of the exploration is that if you have an active neighbor, you don't explore that node, you only explore the neutral node.
yeah.
That's it. That's it. So how will I start? I will start with the first. Right? Now everybody else is in the neutral category. So what am I going to explore?
Neighbors.
All the neighbors. So now you should be able to see that this is nothing but exploring the connected component of it. So let's say this is the that means that there is an edge, means there is no edge. So who are going to explore? All these guys who are connected to it, and we will become inactive at time one. Next time, where will I go? any of these guys will become active.
Hmm.
So any of these red, like anybody who has a red connection will become active.
Hmm.
Rest of them have
So,
remained.
once you done the exploration, like let's say t is equal to 0,
Yes.
and next step, let's say when the exploration will happen, you will again become
We become inactive. Doesn't take any more part in it.
no, but so okay, oh, it's inactive. The status is inactive, not neutral. Yeah. Okay, got it.
It's like it's out of the picture.
Yeah, guys become active.
Yeah, okay.
And rest remain neutral.
Hmm.
You can convince me that if I continue doing this, S of t, what is this problem? So S of 0 or 1. What is S of 1? S is nothing but a number of active nodes. What is S of 1?
Neighbors of 0 to n
Neighbors
minus 1.
having the neutral neighbors, there is a number of neutral neighbors.
What is the distribution?
Oh, the
What's
distribution.
the whole? So now it's no longer independent across time scale.
Sure.
I mean, in our usual branching process, the number of children we are giving birth to will remain independent.
NP.
What
NP.
is not a distribution.
So distribution we have to see.
It's a there is some random variable. How many things I'm adding? So S0 plus something minus the 1. This will get becoming inactive. How much am I adding? What is something, let's say X. What is the distribution of X? So at time 1, it's actually in fact nice distribution, doesn't depend on n minus 1. It's just binomial n minus 1 comma p.
Binomial.
N minus 1 comma p. How many edges do I have starting from B?
Yeah.
Binomial n minus 1. Now I go S2. There's still 2 that I can write as S1. S2. Now it's no longer binomial of n minus 1 comma.
It depends on x one, right?
It depends on A development part. What is
What I mean,
see how many neutral vertices remain at each step? That's all essentially you can impact. Incomplete is impact. At this point, how many neutral vertices were there? N minus 1. And each of them has a probability of being active with P. At time step 2, how many neutral vertices remain? Each of them have probability of having
so okay, I mean the connectivity is there, right?
connectivity is independent of all this. With each pair, I'm putting an edge with probability P. That has no bearing on what is going on.
Now, what I'm asking is that in your graph, you're not assuming entire, I mean, like connectivity to be one, right? Probability
There is no current, nothing. Just
Yeah.
exploration starting from a vertical.
Okay.
So what is the distribution of x2? That's all I'm asking. It's no longer binomial of n minus 1 comma. So how many neutral vertices remain at time step? It has to depend on that.
Yes.
How many neutral vertices?
So let's say
That again is a random.
No, but it's a function of everything you've seen so far. So you should.
S1.
Yeah.
And minus S1.
Preparing x2 is binomial. Something comma 2. That is 2. What is that something? N minus n. Is that correct? Just think about this.
no, I mean
Minus.
One more minus.
I think there will be minus 1.
Okay, good minus. I'm okay with putting anything. As long as you get convinced.
The S1s are your active, right?
Yeah.
And you will have neutral n minus S1.
Okay.
And one is inactive. Okay. So that's it.
Is everybody same? See, inactive don't take any part.
yeah.
They're not. At this time, how many are already active? Yes. They also cannot be made active. Active either remain active or goes up.
Hmm.
They can't be touched. I'm only touching the new neutral case. Our neutral case remains. Who is not inactive and who is not active. That's exactly this number. S1 plus 1. So N minus S1. In general, if you continue this process, you essentially get N. T minus. The T steps, at least I've done T minus 1 steps. The way T minus 1 right in it. S of T are activated. So the potential new bias I can add is only this much on. So now compare this with our branching process. Branching process also had the same recursion, except this XT was IIT, Bernoulli and comma P or this, or whatever that is.
Should be S3 minus.
Yes. So that's the difference between the two processes. One, we know how to control, how to analyze. This is the actual process. Yes. So now think about how do I compare the two. Which do you think is so? We're writing that order, yeah. Same thing with that.
Yeah.
Okay, so this process will be like this. Yeah. Distribution. Give it rest. Next. That's our the possibility looking for that. All the projects are produced independently of what is happening in us. The DLP started with B and S1, S2, S10. The object has to write Sn or to create our this is the comparison. The lower bound, upper bound, whatever bound. In this process, we call it. Yes.
So XT is a decreasing value. Isn't it? I mean the number of so you're basically counting number of
It will also increase here. If you remember, we looked at the time t at which it hits zero.
yeah.
So eventually, that's not the point. Question is how is it like xt? How is it progressing? Think about that. Do you have more chance of giving birth here or there? That's what you should think of. Here there is no bomb. You keep going down the same.
Yeah.
But there, if you increase sufficiently, then you start contracting much faster. Number of nodes you have to infect is also actually.
Yeah.
Here there is no such thing. Yeah. What do you expect to happen? Who should control?
Can I interpret it this way that the mean of each distributions it's
Complicated to think about.
okay.
It's difficult to even count this.
Yeah, that's true.
Look at this process. Xt here is essentially unfettered.
Yeah.
But here, as soon as this becomes large enough, and t is also increasing, it's actually shrinking much faster. So what do you expect? Which process should generate more? For how long? Which process should take longer to terminate?
Right.
Yeah.
Right. So that also tells you the total progeny. Essentially, that the time, the earliest time at which this process hits zero is the progeny size here. Similarly, the same process. In terms of graph, the exploration will stop as soon as you see all the nodes which are connected. Is it clear that this process is actually tracking all the nodes I can reach from B?
Yes.
Yeah, it's clear. Yeah.
But the only thing is that like
In this process as well, I will reach all the vertices from the
No, here I'm even generating the
generated. Yes, that is.
the means the nodes that we will be having in that first graph in first level. After a few levels, we can get those like
No. So think about it. If I can reach certain nodes in S1, and now in the future, the only nodes I'm counting is which can be reached from S1. So if I am B, I can reach S1, and S1 can reach something. I can also reach those something.
yes.
So it's a transitive relationship. That's why all it is doing is to enumerate all possible vertices which can be reached from B.
Okay.
Because in step B, in step 0, I started from B.
B.
So I'm only able to reach anything which is directly reachable by me.
Yes.
Now from that, you are also reachable. It should be reachable. And will terminate as soon as I can't reach anymore.
But it feels like the same node will be getting repeated like in the first level, even if it is
Think about it, it's not reachable. By definition. That's why I'm turning them inactive.
Okay.
So as soon as I become active and infect others, I turn myself.
Yes.
So give me an example here to tell me what doesn't happen by becoming myself inactive. So I start from here and I make this guy active.
Yes.
This guy active. And this guy. Now I am out of the picture. And what happens? I go here. I never go and check this guy because this guy is already in the active state. So even if the edge exists, I don't really count because I've already gone there.
Okay. Okay.
Otherwise, it will be unnecessary.
Yes.
Anyway, I'm going to do this in future. So why should I do it now? So I'll only go to things which have not been seen in level 1. It's just a faster way of doing this. If you also allow that, it will take more time, essentially. So we'll be over counting, and then the time at which I terminate will not correspond to the actual number of. The way we are doing it right now, we will terminate exactly at a time equal to the total number of vertices you can reach now.
Me.
So that is nothing but the size of the vertex.
So what I'm thinking is that let's say you have a node which is connected compared like which is maximally connected in your graph. Maximally connected in the sense that I mean it is like reaching out to most of the nodes.
Let's give you an example. You have everything.
No. Okay, I mean, what I'm trying, I mean,
Yeah, but you can simple example. It might be easier to visualize.
okay. Probably draw 4 nodes and then.
A, B, C, D.
Okay, Okay, so let's connect.
Where are we starting from?
Let's say A.
Okay. And those are given to me anyway. So let's say these two exist.
Okay. There can be a node in between A and B. So,
There's nothing in between. There's no topology.
yeah. So
Do what you want.
yeah. There's a connect.
Okay. No problem. So what will I do? Start with A. Go to any one of these guys in the next step. Now, this will automatically neutral at that point. So I will freeze this.
Yes.
This will become active at that point.
Yes.
But this guy is already active.
Mm-hmm.
So I will not touch
I'll
this.
explain.
So that's why it exactly corresponds to the total number of vertices on connected component of each.
No, what I was thinking is that let's say if you have this a particular node which is connected with most of the other nodes, okay, and so if you start from that node,
See, we are fixing one node. We are not saying connected component of a graph, which is not fixing one node and looking at the connected component of that.
yes.
We are looking at the maximum connected node.
Yeah, so what
For the moment.
yeah, so I was thinking that the moment the number of exploration it is doing at which it stop hits the zero
Yes.
should depend on my choosing the
Yes, yeah. It's a
That's
connected
what I-
component of V.
yeah.
Never said anything. It's a connected component of V.
Yeah.
It will be more than 10.
Yeah, so I'm assuming what I was thinking was that I mean like it depends on how you choose your initial exploration. Yeah, that's what I could.
Simple, right? Suppose it's isolated node.
Yeah.
It better be here. Don't worry. So now we compare this and this pathway. We want to essentially show some kind of domination. That one process dominates the other process. Because I know how to handle one process. This process I think find out everything.
You want to compare this two?
Something is obvious from intuitive point of view. What is that obvious thing? Which process do you think will be smaller than the other process? Left one or the right one?
Smaller left one. Correct.
Now can you show this?
So I have to show this stochastic dominance.
In the
So
And
maybe
what is
that
that
is
one?
created coupling in the
okay, go ahead. You know everything now. You're exactly on the right track. So in particular, so what do you want to say? Probability of the connected component of the B. There is the size of that. There's nothing but the time and place that seems to be greater than equal to some k. Now this side. We find it. Very nice. Usually. We want to compare this versus. What is this quantity? This is the quantity size of the connected component of V will be greater than equal to current variable. You can equivalently think of T. T is nothing but that quantity. T is the time at which my process ST hits 0. Nothing more to explain. That is exactly equal to that. I'm not writing it, but it's an exercise. T defined to be the earliest time at which ST equal to 0 is nothing but the size of the connected component. Hope you're already convinced, but you really want to write it. So now what we want to compare is that in the left side, it hits 0 earlier than the right side. Let's see with probability. Oh, so now complete. It's just one essentially one line. If you write the correct one, there's nothing more to be done. So how do you compare xt prime with xt? That's what we have to do. Can you come up with a function which connects xt prime with xt and show that xt prime is larger than xt? That's all. This is here and here. Somehow show me that xt prime is always larger than xt. There should be data coupling. What are the coupling? You given x and y, you want to show stochastic dominance. You give the x prime, y prime, the x prime is always smaller than that. And we have similarly think of coming with the function where x prime is always larger than x. So think about the connection between the two dimensions. This is binomial n. This is binomial n minus something common. That's your good. So what can we do to this from here? So if you're given two binomials, n by 2p and n by 2p, and I ask you to come up with a binomial n, what would it?
Just make a transformation. Then.
No, take just must. So I gave you two random variables. Binomial n by 2 comma p, binomial n by 2 comma. And the third random variable which is binomial n comma. If I ask you, can you take the first two and create something interesting for my interesting meaning, something comparable to the third random variable? What would you do? Simplest thing.
Add the two.
Add the two. Okay. What would happen? Add the two.
And the two.
Why not? What is binomial n by 2 comma p? How many successors you get in n by 2 track?
Yeah.
Probability p.
Yeah.
So if you have to add two independent copies of it, what should it look like?
Adding these two numbers.
Okay.
Numbers.
Okay.
Please got it. So binomial n by 2 comma plus n by 2 comma.
I see.
What should it look like?
Manual and
Whatever the reason, what to put n slots.
Yes.
Divided into halves.
Yes.
Will you able to distinguish between doing it once or all
Yeah.
slots or doing it half and half? Just one thing, half of them first, then it's there. So it's not getting it. So now I'm going to use the same idea. Over here, what does it look like? The XT plan is binomial over n comma p. XT is over something smaller but same problem. That's the interesting part.
Yeah.
If this was changed, it will be more problem. So what should I do to deliberate XT plan such that it's always larger than XT while respecting the estimations?
I see. So you can just.
It's looking like
Yeah, it's just.
Tell me what should I do? What is remaining? What should I add to it?
P minus 1.
Yeah, plus whatever in mind alpha.
What do you do? Assign something. What is that something? Y difference. The distribution of y.
Binomial P minus 1 is P minus 1.
P minus 1 plus
Plus
ST minus 1.
You have to be slightly careful about this. This is not a deterministic function. That's all. ST minus 1 is a deterministic function.
So it depends on the previous
Binomial
binomial.
distribution.
So it's ST minus 1 is a random variable. You have to be slightly more careful what you do.
Okay.
It's not wrong.
Yeah, I see.
What I'm asking is to be careful what you do. It's not a deterministic function. T minus 1 is fixed. That I can do whatever. So how do I even generate something like this?
Generate something like that.
Because asking you to generate a binomial random variable, which is a random variable itself. You have to use one particular word and allow it to proceed.
Take conditional probability. Sorry, conditional
Condition.
Yeah.
On the number which you have seen. Okay, so yi binomial condition on SI taking values.
Okay.
Yeah.
Now what will happen? What is XI prime distribution? XI, remember, is So xi I have not touched. I'm defining new xi prime essentially. It better have the same distribution as mine. This is right. Then I'm and better be I of course. So this process requires it to be I. Not only the same distribution but independent across. Now tell me what is the distribution xi. This I can define condition on st minus 1. But once I condition and realize what are the outcomes of this? Outcomes are essentially n comma p. So whatever condition I put, whatever value st minus 1 take, what is the resulting distribution of xi?
That's in common period.
So what is happening is your total x. Now depending on the value of si, sometimes you will see yi here. This one, first and second point. This is your second point. Now depending on the value of st minus 1, this will keep changing.
Yeah.
But the overall, the sum is not remains unaffected. That is why xi prime has the same distribution as I wanted, as well as independent.
I didn't get it.
What is going on here? So look at any one particular version of st minus. Let's say st minus 1 is 1.
Okay.
What is this? Is binomial with n minus t minus 1 plus 1. The complement sits here. So
Yes.
you add it together, result is that.
And yes.
So even though I'm defining it as a condition, the whole answer does never depends on the value of st minus 1.
Okay. Yes.
That's so this interval keeps changing
Yes.
side. But the end result, which I'm defining is
Yes.
that. So xi prime is in fact, I think.
So that conditioning thing, why did you ask? Like,
Because otherwise, how would you define this?
Because ST is a random quantity.
okay.
See, for me to define a Bernoulli random variable, you tell me n slots probability p.
Okay.
That is only valid if I can say something which is deterministic. Okay, what is deterministic? Okay, so now I have got so far. Now what? What is the punchline? Now xi prime is summation of xi plus summation. What is the summation? Want to claim that xi prime is always greater than xi. What is y? What kind of values y takes?
Positive values.
Non-zero.
Non.
So xi prime is always greater than x. Now I am back in business. So how do I complete the task? I want this to be. Okay. So this one and two will be connected.
You want a correction in expression?
Which direction? I will leave it to you. You already understood that somehow one is weaker than this thing. So what would you like it to happen? That do you want probability 1 to be larger than 2 or 2 to be larger than
2 to be larger than.
Larger than more. I mean, okay.
1, not number 1.
No, yeah.
Equation. You would like 2 to be larger than 1. Whatever I said, that xt prime is always greater than xt. Complete. So what is equation 1 equal to? So when is the connected component of V greater than K? When the exploration is not stopped until how many steps? K minus 1. So T has to be greater than K minus 1. But what drives T? The interest of time. What is the probability? Okay. is greater than V. Payments. Well, the person is not properly given. But what is the process SP? SP is nothing but all the summation of xi minus I.
Yeah.
Minus items. So it's one. SP prime process. Everything. What is the relation? Tell me. These guys are. Each of them. Yeah. Component by component. What should I write here? For my ST prime process. To compare this, replacing ST with ST prime. Smaller or larger? If this is relationship is true, how long does it take before it remains above 0 for t less than k minus? If these guys are stronger, what happens to this probability?
That probability will be less than equals to
So,
ST probability of ST dash being greater than G.
shock of my life. Which is one is stronger than the other. If this is happening, this is better here. And what is this? This is exactly the probability that t is greater than k. T primes. Which are what? Event to event. This t prime is nothing but the time at which earlier the time at which ST prime becomes 0. The fact that t prime is greater than 0. It has not hit 0, so t prime will be greater. We get one direction.
What I'm thinking is that, let's say, I understand that it depends on the choice of G.
What is it?
The initial.
Okay. All we're doing is V.
Yeah.
V was the original node we started with.
That is single.
Yeah.
So typically, in the branching process, you're starting with that one particular node. You can name it V or whatever you want. All we are saying is that the number of projection or the number of connected components are related in such. So currently, we have not said anything about what is happening in the whole graph. All we have said is what is the size of the connected component of one particular. Why is it interesting?
Why is it interesting?
I think that's where you are coming back again and again.
Yeah.
So let's just get to that. But why is it interesting to look at one particular node and its connected components? So suppose if I pick an arbitrary wheel and show that the size of its connected component is very small.
Okay.
What does it tell me about the whole graph? How many possible V's are n? So if I show something that the probability with which something bad is happening with sufficient large probability, it will happen for every other node. That's what we are.
Yeah. So you can say that the graph is not very much connected.
No, connectivity we already show. Now the whole we're trying to do is to look at the connected component, the size of the connected component of one particular vertex. One particular vertex is useless. Which means a bad vertex, bad distribution. But then how many different nodes are available? So the probability of something happening bad is greater than 1 by n. Even if you were to put a union bound, all this is goes. That can be spread over the whole network. That's what we are. So that's why we're looking at one particular. You can't simultaneously look at different vertex because their collection is super convoluted. It's super convoluted because if I ask you give me the connected component size of one node and another node. They're highly correlated.
Yeah.
That's why I'm not adding them simultaneously. Because they could touch somewhere, and then from that point onward, they just go the same way. So we're keeping every node separate. Painting each node essentially is trying to create a tree, not a tree. And trying to see how large is connected component. So if you can control it sufficiently, then you can control it for the whole. That's the whole process.
Can it happen that the independent one, the binomial branching process, it could die here earlier for a particular realization?
Yeah,
It could happen.
particular realization we don't care.
Right.
We're looking for probabilities. What is the probability that the size of the connected component of Stochastic graph and the size of the progeny in the branching process? In probability, the realization, nobody will. That kind of question doesn't exist. Look, so I don't have time for the upper bound. We'll do the upper bounds. This is a lower bound. Like this process is upper bounded by a branching process. You also want to do something smaller, okay? So that I can sandwich it between two branching processes. So that won't be as clean as this. That will actually start depending on. So I will get to looking for you. Looking for a distribution of the function of k. We will exactly able to connect it to k. When we look at something lower, it will start depending on k. Then this process I'm defining, k will start appearing. That won't be as clear as this. So the branching process I want to look at the distribution is n minus k component. So every time as k increases, k increasing here, I'm looking at smaller and smaller number of the distribution that we should. Okay, what is that now? See, this was the upper bound. That this process is going faster than that. Now I want a process which goes slower than this. So this clearly is not over. What is the correct way to think about it is that if k is large here, I want to shrink that process. The number of children I'm going to produce here is going to be not here. The other way to think about it would be n by k, but that's not required. From it is n minus k. That also is, if you can, all you need to do is the reverse direction. Xi is the same thing. So if there is the same process. Xi is what I define. It's a binomial with n minus k comma p. That's what I do. Okay. Let's start here.